Welcome to this really short video introducing how we can use all the concepts we've been discussing so far in 1511 and use these to create the linked list structure. This video is really just designed to introduce you to linked lists specifically for assignment 2. So let's get straight to it. Here we have an array. Now, we've used arrays a lot. You've used them in assignment 1. They're really great data structures. We can store some data in each element. The elements are in a contiguous piece of memory, which means if we want to iterate through all the elements, we simply just have to iterate through one by one sequentially and access the data there. If we need to grow the array, we can call the function like realloc, and we can say, well, I want room to store those elements, in this case, 6 times. And so we get enough memory required to store all the elements that we need in memory. Really nice. There's actually some limitations with array. Let's think about it. If we're extending our array often, we might run out of enough contiguous space in order to simply extend the memory allocation, which means the operating system will need to allocate the memory somewhere else in the heap. There's also another problem. Have a think about what if you want to add an element to this array in the middle of the array. So you've got some data in this array and you want to put an element inserted into the middle. What would you do here? It's actually not that straightforward. We would have to reallocate to some memory that's big enough to store the new data and move every element one up so that there's an empty spot in the array and put it in the middle. This sounds like a lot of work, and it is a little bit of work, computationally speaking. And so we look to other data structures that allow for these sort of operations much more easily. So imagine if instead of having contiguous memory allocations for arrays, what if we could split up each element into different positions in memory so that we didn't have to worry about it being contiguous? And that's what a linked list is. So a linked list is simply where each element of your data structure doesn't have to be contiguous. So it's still all there in the heap and we can access each element. Now if we want to add a new element, we simply do a new malloc just for a single struct and add it onto the end of our linked list. It's really cool because there's no need to reallocate the entire, size of all the elements that you have. You can just allocate for one more allocation. So how do we actually do this? Like our dynamic arrays, it all occurs on the heap. And here's some code in C for creating a linked list. And if you have a look closely, there's nothing new here. It's using everything that we've used so far. Let's run through this code. First of all, we're defining a node struct. So this is just a normal struct, and we're calling it a node. The node is the term that we use for each element in a linked list. It's got 2 things in it. If we look at the second on line 6, we have just some data, in this case an integer, but that could be whatever we want to store. And if you look at line 5, we have something very interesting that makes linked lists possible. All we're storing is a pointer, because there's an asterisk there, to another node. And we're calling it next. So that's a pointer to a struct node. Interesting. Let's see how that works. So in main, let's make 3 of these nodes. To make a node, we're just mallocing the size of one of those node structs. Pretty straightforward. And we return back a pointer to that heap allocation, and we assign it to a variable called head, which is a pointer to a node, right? And so if you look on the right-hand side of the screen, we have in the main stack frame, this head pointer, and it points to the heap where there's some data allocated for an integer and a pointer to another node. We do that 2 more times. In this example, I'm storing the pointers to each of them in 3 separate variables, but you may not need to do that. All right, this is not a linked list. This is just 3 completely separate heap allocations. So how do we actually turn this into a linked list? Well, first of all, let's put some data in there. So I'm putting the number 1 into the first allocation, number 2 and number 3 into the next 2. And here's where the sort of magic happens. Let's break down line 22. So we take the head and we follow its pointer to the heap where we have int data of 1 and then that next pointer. And we say that that next pointer should point to wherever linked list 2 points to. And so that green arrow gets added, and that next address points to where the second node was created on the heap. That's pretty cool. Let's do that again for linked list number 2. So the second node's next pointer points to wherever node 3 is, where the data is 3. That second green arrow that just got added. And finally, to wrap it all up, we say that that third node, the last node, it points to nothing, so null. We just assign null to next. And that is a linked list. We have actually created a linked list there. So if you take away main, that's what's left on the heap. Some data, and a pointer to some more data, and a pointer to some more data. How do we actually, iterate through a linked list? So if you look on the code on the left, we've added some lines of code from lines 26 to 31. Let's just blow that up. And let's talk about how we can iterate through. So we'll make another pointer in the stack called current, C-U-R-R, and we'll say, hey, point to wherever head was pointing. That's the start of my linked list. So it will point to the heap where the first node is. Then we have a while loop, and this is a normal while loop, but we're not using an integer here. We're doing something different. We're just saying keep looping while current is not pointing to null. So at the moment, if we follow current's pointer, it's pointing to a node that's not null. So this will continue. On this line, we're just printing out the data at that node, which is current.data. And then we say, well, make current now point to wherever current's next was pointing to. So current now, and you just saw the arrow move, will now point to the second node. Done. The while loop executes again. Is current pointing to null? No, it's not. Print out the data, shift it forward. It's still not pointing to null. Print out the data, shift it forward. Now current.next in the third node was pointing to null. So current will now point to null, which will make that while loop fail. And we've now just iterated through our linked list. And that's it. That's a really simple introduction to linked lists. So if we go back and look at this linked list example from earlier, have a think about how could we add a node in the middle of our list? Maybe that's a question for you, but if you look pretty simply, we could just rearrange where those pointers are pointing to. But the really cool thing is we don't need to reallocate the entire size of the linked list, which we would have to do if we were using arrays. That's what makes linked lists really efficient for certain types of problems. And that's a really quick introduction to linked lists. We'll talk more about linked lists in more lectures, but this was just to help get you started for assignment 2.